I really liked his paper on example of local cohomology model with infinitely many associate primes. So today he's going to speak on local cohomology in prime characteristic generalized fractions approach.
Okay, thank you very much. So I'm afraid I don't have any counterexamples today, but I'm going to show you some other interesting stuff. So what I'm going to show you is joint work with Rodney Sharp, who unfortunately cannot be here today. So let me start by telling you what the plan for the talk is. So I'm going to show you some things that many of you know very well, but if you don't, that's going to be a taste of the subject. So I'm going to tell you what local cohomology is, and if you haven't seen this before, just enjoy the taste. I'm going to show you some tools that people use in positive characteristic, uh, specifically the Frobenius functor. So again, if you haven't seen this before, it's just a taste of things to come, if you want. I'm going to tell you about Lubetnik's Finite F Modules. And then I'm going to show you some things that I doubt many people know about, except for one person Hussein Zachary, which I'm very happy to see in the audience. He's probably going to correct all my mistakes about these sharp Zachary generalized fractions. And then I'm going to link all these four tools together. And I'm going to show you can take something very complicated like Lubetzik numbers, and you can give an algorithmic description of them. So you can come up with a Macaulay 2 program that you press a button and you get Lubetzik numbers in characteristic P. So that assumption is crucial here. Okay, so let's start with local cohomology. So we're going to have an R floating around this talk. It's always going to be a commutative ring. And let me start by defining a functor, which I'm going to call gamma I, which is applied to various things when I is an ideal of your ring R. And you define it to be the direct limit of homing R modulo the kth power.
We are unable to say, okay, no.
Sorry, I need to press something for this topic. So gamma I applied to a module is what you get by applying the direct limit of homing R mod I to the power k into that module. And what you're getting out of this is, to apply this to a module, is the element, the set of all the elements in the module which are killed by some power I. And if you think about this for a moment, you're going to discover that this is covariant and it's left exact. And then we do to this covariant left exact functor what we normally do, which is to look at the right derived functor of this functor gamma I. And what we're getting is what we're going to call the local cohomology modules, the Jth local cohomology module is supported I. So this is the right derived functor of this gamma I just introduced. So we're going to be looking at local cohomology of various things, and our aim at the end is to take some local cohomology of a local cohomology module, which is local cohomology modules are enormous objects that either zero or typically not finely generated. Now we're going to take local cohomology of a local cohomology module, and we're going to say something intelligent about it. Okay, let me remark something here. So I can compute the same functor gamma by doing something slightly different. If I give you any other sequence of powers, which I'm calling I subscript k here, with a property that are cofinal with I to the kth power, then you can compute this local this gamma functor as the direct limit of homing R mod ik into your modules. What I mean by cofinal is that for every k, there exists an alpha of k such that I alpha k is inside ik and the other way around. For every k, there is a beta which depends on k, so that I to the beta k is inside I of k. I to the beta k is inside I to the k. And we're going to be using this, we're going to be computing this gamma factor by using slightly different sequence of ideas. Okay, so now we know, or at least we're supposed to know now what local cohomology modules are. Let me tell you some things about characteristic P. So there are some things we can do in characteristic P that we cannot do in general. And we can do these things because in characteristic P, if we raise the sum to the fifth power, we get the sum of the fifth power. And what does that allow us to do? We can start with any ring of characteristic P, which again I'm calling R, and I can define a new structure on R. So I'm going to call it F lower star R, which is an abelian group. It's the same thing as R. But now I'm going to endow this abelian group with the bimodule structure. There's going to be a right R module structure and a left R module structure. So the left R module structure, which I'm describing here, is the regular, the usual R module structure on R. So an element A in R multiplying an element F lower star R in F lower star R gives you F lower star A times R. But then if I take a B in R and I multiply this element on the right by D, then it jumps into the F lower star with a fifth power. And the fact that P1 to the P plus P2 to the P is P1 plus P2 to the P tells you that this definition gives you a plausible, a correct action of R on F lower star R as a right R module. So now that we have this double behavior of F lower star R, we can define a functor. And what is that functor going to be? It's going to be taking something and tensoring it with F lower star R on the left. And when you write this, the production of this tensor product uses the right module structure. But after you create this tensor product and you want to view it as an R module, you can treat this as an R module via the left R module structure of F lower star R. So the untwisted action on the left of R and F lower star R. Okay, so let's see how this looks like. So let's, instead of carrying around F lower stars everywhere, let's just identify the elements of F lower star R with the elements of R. So if you look at this tensor product, defining the Frobenius functor, and you multiply it on the left by A, it's going to give you this. On the other hand, you can also multiply R tensor M by A by multiplying M by A, in which case you get that. And now if you want to make this A jump over the tensor symbol here, you have to remember that you're using, to define this tensor product, you're using the right module structure of F lower star R. So when you make this A jump over the tensor, it becomes an A to the P. Okay, so this looks all very strange. Let me show you an example that may clarify things a bit. So let's take an ideal I in R. And let's compute the Frobenius functor applied to the R module, the cyclic R module R mod I. So this is what we need to do. And when you do this tensor product, what you're doing is you're multiplying, you're taking the quotient of this by I multiplying on the right F lower star R. When you ask yourself, what is F lower star R multiplied on the right by I. And what you're going to get is the ideal generated by all the fifth powers of elements in A. This is the ideal generated by A to the P when A is in I. And then you say, so what's this as an R module, as a left R module? Well, when we do that, we identify F lower star R with R, and what we're getting is then this. So this example is terribly important because we're going to come across these things again and again. Let's give a name to I to the square bracket P. This is the Pth Frobenius power. Okay. So this is the kind of things that people in characteristic P like doing. They like applying Frobenius functors things. And now this is often very useful because of this theorem by Kunz from 1969 or so. It says the Frobenius functor is exact if and only if R is a regular ring of characteristic P. And we are going to be working in this setting. Eventually, we're going to be looking at what happens over regular rings of characteristic P, and that's going to be the background of the construction of finite F modules that I promised to show you how to construct. So now let's start combining the various strands of the things I'm telling you about. Let's try to compute local cohomology in prime characteristic. So I want to construct the local cohomology modules that supported the ideal I. And how do we do that? So we said it's a right functor of something or another. So let's choose an injective resolution, which I'm going to call E. I'm going to take an injective resolution of R, and I'm going to compute for you the local cohomology modules that support the I of the R module R. So how do I do that? Well, the recipe was take a sequence of ideals which is cofinal with the powers of ideal I. Look at home of this sequence of R module of the sequence of ideals with your injective resolution of the thing whose local cohomology module you're trying to find. Look at the direct limit of that as you go over this sequence of ideals cofinal with the powers of I, and take cohomology of that. This is the definition, more or less. Now we have cohomology of a direct limit, and cohomology and direct limits commute. So instead, we can look at the direct limit of the cohomologies, and this is what we're going to get.
Sorry, Moty, your voice is breaking.
Oh, is that okay now?
Yeah, voice was breaking. Do you have some earphones that you can use? Because once in a while, the voice is not clear.
Okay. What am I going to do?
Can adjust some volume or something.
Do I sound okay now?
It is not breaking right now.
Okay.
But if
I
you
think
try,
I'm going to raise my voice. If it happens again, then let me know right away, and then I'll rush and I get something else. Is that okay?
I can hear now, but if you have earphones, you can try and it may improve.
Okay, so give me a minute.
Okay, can people hear me?
Yeah, now it is very clear. Yeah. Thank
Okay,
you.
wonderful.
Yeah.
Great. So let's see where we stopped. So I want to compute this local cohomology module, these local cohomology modules. Here's the definition. We end up looking at the cohomology of a direct limit, and I claim that that's the same thing as the direct limit of the cohomology. And then we look what's inside the cohomology now. Huh. Sorry. What is a cohomology now? So we're taking the cohomology of the result of applying hom of R mod I to the Frobenius P to the E into this injective resolution, but that's computing for us an X. So what we're looking at is the direct limit of this X. And now we look at this and we say, we recognize what this is. This is the result of applying the Frobenius functor E times to R mod I. So I'm going to denote this repeated application of the Frobenius functor this way. So this is what you get by taking F R of F R of F R E times. And the same thing for R. You can think of it as being the iterated Frobenius functor applied to R. If you want, you can get this by taking I is equal to 0 in the previous example. So now we end up with a direct limit of X of the ith Frobenius functor of something to the ith Frobenius functor of something else. Now we remember that the Frobenius functor is exact. So we can pull the Frobenius functor outside. And then we're left with the direct limit of Frobenius functors of this nice finitely generated R module. And that's another way of writing the local cohomology module with supported I. So this is an interesting example because it's the elementary or the seminal example behind the construction of finite F modules. So let me show you what I mean by that. So let's introduce now the concept of finite F modules. So we're going to be working now over a regular ring of characteristic P, which I'm still going to call R. And I'm going to define for you what is an finite F module. So it's going to be an R module, which I'm going to call curly M, which is given by a direct limit. And what is that direct limit? So you start with a finitely generated module M, here it is, and you start with some R linear map between M and its Frobenius functor. And now you take this map between M and its Frobenius functor, and you apply to it the Frobenius functor. The result is going to be a map from the Frobenius functor of M to the second iterated Frobenius functor of M. And you can keep on doing this again. So you apply the Frobenius functor to this map to get this map. And you get a direct limit system whose direct limit you can define to be something which I'm calling here curly M. So what is an finite F module is an R module which can be written in this form when M is finitely generated. Now let's introduce some terminology that we're going to be using several times in this talk. So given an finite F module, and when you write it in this form, and there may be different ways of writing this in this form, then you can look at the map that you see here, and you call it a generating morphism. A generating morphism for M. And if this generating morphism happens to be injective, you call it a root. So what's the connection between this definition and the example I just showed you? So before, the example I just showed you says the following. this local cohomology module is a direct limit of x r mod I to the p to the e into r. And now I claim that this direct limit looks like that. Because if you think about, if you go back to the calculation in the previous slide and you think about what are the maps between these various x, so what you're doing is you're starting with r mod I, then you have a surjection from r mod I to the p into r mod I, and then the map from the first x to the second x you're going to obtain by taking a free resolution or minimal free resolution for r mod I, and then you obtain a free resolution for r mod I to the Frobenius p by taking the Frobenius functor of that. And then you home into R and you take cohomology and you get the X. So that gives you a map from, let's see, from X R mod I R to X R mod I to the PR. So let's call this map U. And the next map I claim is the Frobenius functor applied to U. Because how do you get the next map? Well, now you're going to look at R mod I to the P squared. You're going to look at the quotient map from R mod I to the P squared to R mod I to the P. And that's going to be inducing a map of the second Frobenius functor of the resolution of F to the first Frobenius functor of the resolution F. And the end result is that these maps between the resolutions now are induced by taking the Frobenius functor of these maps over here. So when you put everything together and you look at this direct limit of x, what you're seeing is an Finite F module. This is a finitely generated R module that maps onto its Frobenius. This is the Frobenius functor of the previous x. And then the next step you're going to get by taking this map and applying Frobenius to it and getting to the second Frobenius functor applied to the x and so on, and you end up with something of this form. So these are finite F modules. Okay, I don't know what's the custom here about questions, but maybe I should stop at this point and see if anyone would like to ask me anything. Let me check that I still have an audience. Can people still hear me?
I don't see any questions in the chat box.
Okay.
Yeah. We normally have questions at the end. Yeah.
Okay, so let's continue. So I just convinced you that local cohomology modules of the regular ring of characteristic P supported at I, these are finite F modules. And this is very good because now the great contribution of Lubeznik, other than defining these things, was to prove some interesting theorems about finite F modules. And I'm going to show you two, and there are many others. But the first one, the first theorem over here, was the main motivation for everything. So people were wondering about the associated primes of local cohomology modules. And now they solved this in more generality. He said if you have any finite F module, and if you choose any root, and I should say that given an finite F module that is given a generating morphism for an finite F module, you can always use it to produce a root for it. So finite F modules have roots. So if you look at the root of your finite F module, which is going to have this form, and if you want to know what are the associated primes of this Finite F module of the direct limit of this and its Frobenius functors, then the associated primes are the same as the associated primes of this finitely generated module M. And in particular, and this is what people are really interested in, the set of associated primes of Finite F modules is finite. So this local cohomology modules I just showed you, the set of associated primes is finite. And let me show you, so we're not, this was a motivating theorem for the development of this theory, but we're not going to do very much with it. Let me show you something that we are going to use at the very end of the talk, which is this other theorem that says, if you want to know what is the dimension of the circle of your Finite F module with this root over here, then the dimension of the circle is the same as the dimension of the circle of the root. And this is a particular case of another statement that you can make about bus numbers, but I'm not going to go there. This other statement says that, just as in the previous theorem, the one about associated primes, the bus numbers of Finite F modules are also finite. In the case of bus numbers associated with the maximal ideal in this local ring, then you can actually read it off the root. Okay, so now I told you about local cohomology. I told you why characteristic P is nicer than other characteristics. And then I show you Lubetzinck Finite F modules. So these are things that most in the audience probably know very well. And now I'm going to show you something that not many people know well, and it should be known much better, because each time Rodney shows me what you can do with generalized fractions, I discover something surprisingly useful and nice. So the problem with what I'm going to describe to you now, and I'm going to show you just a simple setup of the Sharp-Zachary generalized fractions. Zachary as in Hossein Zachary, which I think is in the audience. So the problem with, the only bad thing about generalized fractions is that there's a lot of technical stuff that one needs to do first. So let me first tell you what these things are, then let me tell you what the technical stuff is. So what we're going to do is going to be a generalization of localization. And what's going to play the role of an analog of denominators. So we're going to do an analog of a localization at one element. So now instead of localizing at one element, we're going to fix a sequence of elements, and we're going to take as a set of denominators the powers of these elements in this sequence. So what are going to be these generalized fractions? So we're going to start with an R module, and we're going to find its generalized fractions. So we're going to denote this with u to the minus n applied to the R module M. And what this is going to be is going to be a new R module. So I have to tell you first what the elements are. So the elements are going to be equivalence classes of elements in this form when the numerator A is in your module M and the exponents of the various f's in this sequence are greater or equal to 0. And now, okay, so we can write all these symbols, and we then introduce an equivalence relation, and the elements in this module of generalized fractions is going to consist of equivalence classes of these. So what is this equivalence relation? And again, I'm showing you a special case of this construction. In general, one needs to do something more general. So the relation, so we're going to declare this element, or this symbol, to be the same as that symbol if, so first we want to have the analog of finding a common denominator. So we're going to look at some powers of f1 up to fn, which I'm going to call f1 to the gamma 1 up to fn to the gamma n. And then you want to be able to transform this denominator into this other denominator, and the same for that. And you do that by multiplying this column by a matrix H with entries in R. And you do the same thing by multiplying this sequence of in the denominator by another matrix K. And you want this to give you the same denominator, the same sequence, which is the denominator of a new generalized fraction. So you want to find these two matrices, which in addition to having entries in R, they have to be lower triangular. And now the condition, going back to this, the condition of these two symbols being the same is that if you multiply the determinant of the matrix H by A, and you subtract the determinant of this matrix K times B, what you're getting is an element in here. Notice that I don't go all the way to n here. I go to n minus 1. Okay, so why are these things technically difficult? Because now you have to do some work to show that this is an equivalence relation, and then you have to show that the natural way of defining operations is well defined. And since the definition of this equivalence relation is quite complicated, each time you want to write something, you have to be careful that what you're writing is well defined. But we're not going to do that. I wish Rodney Sharp would be here, and then he would just show us how easy all it is, but I am still not very conversant with this. But now let's try to use this construction. So again, it's a construction of, which is a generalization of localizing at one element. What can we do with it? Well, before I show you what can we do with it, let me show you an example of one calculation that I do know how to do. So with the same notation as before, let's have a look at the symbol A over this sequence of powers of F. So this is 1, we should say n minus 1 instead. So the special thing about this sequence of the denominator is that it ends with 2 1s. And then I claim that this symbol is 0, and by 0 I mean 0 over f1 to the alpha 1 up to fn minus 1 to the alpha n minus 1, 1, 1. This is one way of writing the 0 element in this module of generalized fractions. So let's see if I can convince. This is the only calculation I'm going to do with generalized fractions in this talk. Let's see if I can get this right. So let's have a look at the this element 1 here, the penultimate element 1 there. If you go back to the definition of what does it mean for two symbols being the same, you need to have some difference of elements in M being in the submodule of M, which is given by this. In our case, this, with a different subscript, this is just saying 1 times M. So this thing, which is always in M, is always going to be in M. So this is telling you that the generalized fraction that I wrote here is going to be equal to 0. And this simplest of examples with generalized fractions, it looks like a manufactured example so that I can show you that I can do calculations with generalized fractions. Actually, it's going to be very important, and I'm going to show you where it's going to be very important. But before I do that, in this example, you can easily convince yourself that this is 0 by taking H and K to be identity matrices. But before I show you that this example is actually very useful, surprisingly useful, let me say something else about modules of generalized fractions. So you're going to have faith in me, because I'm not going to show you why this is true. So let's have a look at this module of generalized fractions that I just constructed for you. Then just as in the case of localization at one element, you can write the localization of at one element as an ascending union of fractions in which the denominator is higher and higher powers of the thing you're localizing at. So the same thing you can do with generalized fractions. So here, when I write this, I mean the generalized fraction 1 over this sequence. And then what I'm writing here is the submodule of the module of generalized fractions generated by this one element. And we get this module of generalized fractions as the ascending chain of these submodules. And the additional information that is going to be very useful for us is, sorry, we just lost something here, is that we can write down what this cyclic module is exactly. So it's a cyclic module. It's going to be the quotient of the ring R, and it's the quotient by this ideal, which I'm calling the low limit closure of the powers of the Fs. And this low limit closure of the powers of the Fs is defined to be the stable value of this ascending chain of ideals. And the important thing is that in characteristic P, so up to now when I talked about generalized fractions, I didn't assume anything about the characteristic. But now if the characteristic is P, then this can be computed effectively in polynomial rings. So if you give me this sequence of Fs, I can, sorry, what I meant to write is not quite this. What I meant to write is this. Yeah. So, and then if you want to find, sorry, and then if you want to find the low limit closure of this p to the I powers of the F's, you can just take the Frobenius power of this low limit, and you're going to get surprisingly and very nicely the right answer. So what I want to say, the moral of this slide is that we know how to compute this. Know how to compute. In characteristic P. Okay, so now let's see. We know, I showed you what finite F modules are, and I'm showing you generalized fractions. Now let me show you a connection between the two, and the connection is in the form of this theorem. So you can look at the...
There is a question in chat box.
Sorry?
What is the exponent of the Fi in the definition of low limit?
So here we're taking a union over i's, increasing i's, and this is computing the low limit closure of the sequence,
I mean
the ideal generated by f of the...
Okay, I meant on the left side. The correction that you made, in the correction that you made, Fi to the P, is that what is the exponent?
Sorry, it's just F1.
Just F1. Okay, thank you. Thank you.
Okay. So now let's go back to finite F modules and ask ourselves, I just defined a new object, which is this module of generalized fractions. The module of generalized fractions applied to the ring R. And suppose that we're working in characteristic P. Does this happen to be an finite F module? And the answer is yes. So here is a submodule of u to the minus nr, the one generated by this one fraction. And now you can look at the Frobenius power of this module, and it happens to be generated by this other fraction, in which all the f's are raised to the p. And this injection, this inclusion, is a root. It's a root for this as an finite F module. Okay, so we look at this, and we say we can compute u to the minus nr, the modulo of generalized fractions of R is the direct limit of this first row, we know that each one of these cyclic modules is isomorphic to these quotients here. And now we can ask ourselves, when I look at these isomorphic versions of these cyclic modules, what corresponds to this inclusion? And these maps over here are given, the first one is given by multiplication by the product of the f's to the p minus 1. The next one is going to be given by multiplication by the pth power of this product, and so on. So we have a good way to describe a root. So this is a root for U inverse, so U to the minus NR. Okay, so let's go back to this very simple looking example I gave you before, in which I showed you that an element, a generalized fraction, is here, and let's see how we can use that. But before I do that, I have to introduce another concept that, again, if you haven't seen this before, it's going to look very strange. So I'm going to define what is an I filter regular sequence. So we are going to have, now R doesn't have to be characteristic P, it doesn't have to be regular. Let's take an ideal I in R. I'm going to call a sequence of elements, potentially infinite sequence of elements, F1, F2. I'm going to call it an I filter regular sequence. If whenever you localize at any prime that does not contain I, you get a possibly improper regular sequence. Now, it takes some time to figure out what this is all about, but it's a good exercise. If you haven't seen this before, convince yourself that this I filter regular sequence exists, and you can take them to have any arbitrary length. And the point is that when you are constructing these I filter regular sequences, what they're trying to do is you're trying to avoid choosing an element in the union of the associated primes that do not contain I. Now, if you're looking at a union of primes that do not contain I, their union is not going to contain I. So they're never going to be able to cover the entirety of I, so you can always choose an element outside, and that gives you an additional element at every step. Now, for our purposes, now that I told you what I filter regular sequences are, we can just think of them as being sequences of elements with magical properties. And here's a magical property for our purposes. So let's look at the construction we had of generalized fractions. And now let's take the f's, f1 and f2 and so on, to be an I filter regular sequence. And then we are going to construct a complex. So what is the complex? So the complex is R injects into elements of the form A modulo the sequence f1 to the alpha 1. And now I'm going to look at U2 of R. So I fix an infinite I filter regular sequence beforehand. So now I can talk about a B over f1 to the beta 1, f2 to the beta 2. So I'm looking at all the generalized fractions of this form in here, all the generalized fractions of this form in here, and so on. And now I'm going to construct a map going from one of these pieces to the next one. And if I'm going to go from the nth entry in this sequence of maps to the nth plus 1, what I do is the differential is going to be, you take this generalized fraction here, and you extend the sequence into the denominator by adding the element 1. And now, what happens if you go along this sequence of maps twice? What happens if you apply these differentials these twice? Then you're going to end up with a generalized fraction in which the denominator ends with 1, 1. And the example, this very simple example, the only example that I'm going to show you of a computation, told us what you're getting is 0. So what you're getting here is a complex. So what's written here is a complex. And now, what is the magic of I-filter regular sequences? It comes in the form of this theorem by Hashia-Marnesh, Salarian, and Zachary, which is that if you look at the cohomology of this complex I just defined for you, what you're getting is the local cohomology modules of R with supported I. I being the same as this I, the I which you use to construct this I-filter regular sequence. Okay. So let's see if we can start putting things together. So let me skip this because I'm not sure I'm going to have enough time. So let's try to put all of this together and do a calculation. So the calculation I'm going to do, and what I mean by calculation is I'm going to run something, if I have time, I'm going to run something on Macaulay 2, and you're going to get an answer, so that you can't get more explicit than that. So what I want to compute now is Lubetzik numbers. So what are Lubetzik numbers? So we're going to start with a regular ring, a local regular ring, which I'm going to call Rm of characteristic P. And then I'm going to fix some ideal, which I'm going to call I. And then I'm going to show you what these Lubetzik numbers are. So Lubetzik numbers come indexed with two indices, I and J. So the IJ Lubetzik number of R mod I is equivalently, you can describe it in two equivalent ways. So the first equivalent way is as a bus number. So you look at this local cohomology module with supported I, the dimension R minus J local cohomology module with supported I of your ring. And then you ask what is the ith bus number corresponding to the maximum ideal M. So what is that saying? It's saying you take a minimal injective resolution of this gigantonormous R module. You go to the ith place in this injective resolution. What you're going to see there is a direct sum of injective modules of the form R modulo prime. You count how many injective halves of R modulo M do you see there, and you call that number this mu I of M and this local cohomology module. Now, I hinted at the fact that this number is finite. And one way to convince yourself that this number is finite is by looking at the second equivalent definition of this, which is it's the dimension of the circle of the ith local cohomology with supported M of this complicated local cohomology module. So what we're doing here is we're looking at a local cohomology module, is in the title, of, well, in this case, of another local cohomology module, but which happens to be, you can do this for Finite F modules in general. And in this particular case, either the bus number or the dimension of this circle is what we're calling the ijth Lubetzik number of R mod I. Now, I'm throwing lots of things at my audience, so I'm sure there are people wondering what local cohomology is for, and that has an answer. And people may be asking, what are Lubetzik numbers for? That has an answer too, but I'm not going to get there. So if you haven't seen this before, take this as an invitation to look into this. Okay, so what I'm going to do in the remaining time of this talk, which I'm not quite sure how much it is, I'm going to show you an algorithm for computing these Lubetzik numbers. Okay, so how am I going to do that? So the first step is a simple observation. So let me just check that I still have an audience because I can't see anything. Can people still hear me?
Yeah.
Yeah.
Okay, good. So here's a simple statement, which is, suppose that you have two finite F modules. So I'm going to call them curly M and curly N. Then you can find generating morphisms for these finite F modules. And now you can ask yourself, how about the tensor product of curly M with curly N? Then it turns out that this is also an finite F module. And it is an finite F module because it has a generating morphism, which is the tensor product of the generating morphisms for M and N. So the only place where you have to work a bit is just to show this isomorphism here, but it's just a matter of getting the definitions right. Okay, so we're going to be using this. And now let's compute the basic numbers. Let's start with this inner local cohomology module, curly N. And what we want to do is we want to look at an ith local cohomology module. We supported the maximal ideal M of that. But before we do that, let's fix a root for this local cohomology module that by now we know it's an finite F module. And now I want to, actually, I think I want to go back and I want to tell you something that I forgot to tell you before. So when I showed you the magic of filter sequences, I want to make the magic more impressive. So I'm going to go here and I'm going to put any R module, non-finitely generated if needed. Okay, so this is truly magical. This is what we're going to have to use in what we're going to be doing next. So I want to use this magical theorem by Hashai-Nesh and Salarian and Zachary to compute something. And to apply the theorem, I'm going to have to find an M filter sequence. Remember, I want to find the local cohomology with supported M of this gigantonormous module. So I want to find an M filter sequence of curly N, and one can convince oneself that if you find an M filter sequence of the root, that gives you an M filter sequence on the entire finite F module. Okay, so now how do we compute the mth local cohomology? So we're aiming to compute the ith local cohomology with supported M of this curly N. Well, the magic of filter sequences is telling us we're going to we have to apply the complex to N, the complex which we build with filter sequences, and then we take cohomology of that. And when we ask ourselves what is that giving us in this context, so you can describe now things in terms of generating morphisms. So you're going to get a new finite F module, which is the one I just erased, which is the finite F module, which is the ith local cohomology module with supported M of hi of N. This had a root, and we compute local cohomology with supported M by taking generalized fractions of this module and then taking homology between some maps in a complex of generalized fractions. And when you look at what you end up using the previous lemma that says that a tensor product of two finite F modules as a generating morphism given by the tensor products of the generating morphisms, what you end up is with a finite F module. So this is an finite F module which has this as a generating morphism. And now we go back and we can start writing things in terms of something that Macaulay can understand. So what do we end up with? So this is how, so let's introduce new notation, which is GI, which is the sequence F1 up to Fi. So if you look at the map from here to here there, say, this is the map that gives you, let's see, U minus 1 of R as an finite F module. This is generating morphism for it. But now what we want to do is we want to take the cohomology of the rows, and then we want to take the direct limit, the vertical direct limit of the cohomologies of the rows, because this is how you compute the cohomology of this complex of generalized fractions that gives you the local cohomology module with supported M. Remember that these were M filter sequences. Okay, so how can we now compute the double local cohomology module, which is HI with supported M of H dimension R minus J with supported I of R? So we have to take the cohomology of the rows, and then to get the answer for this I, we look at the ith column, and we look at the direct limit of the cohomology of the rows. And at this point, we say, but we understand everything here because we know we wrote this explicitly. This R modulo the sequence F1 up to Fi was the quotient of R by Ci, which is the low limit closure of F1 up to Fi, and we know how to go from here to there. It's given by multiplication by the p minus 1 power of F1 up to Fj, and we have the map theta that goes from n to the Frobenius of n. This is the root of what we call curly n, the finite F module curly n. So now what we need to do is we have to find the cohomology here, and we have to find the cohomology here, and then we get an induced map of the cohomologies, and this is going to be a generating morphism for the direct limit, the vertical direct limit of these maps between these cohomologies. The good thing is that we know how to compute everything. So now that I've written things in terms of these ideal CIs and these maps pi i's and thetas, I know what all these maps are. I can go to Macaulay and say, compute this cohomology here, compute this cohomology here, give me the induced map from this cohomology to this cohomology, and that's going to give me a generating morphism. And that's it. So this is the end of the theoretical part of this. Now let me show you a calculation so that you see that this is actually useful. So to show you this calculation, I'm going to take an example. So I hope that people can see an example. Can
Yeah.
people see a matrix? Okay. So this is an example of a calculation of a Ljubetzig numbered array of some ring. So here's the ring. Now, these Ljubetzig numbers, they are defined in all characteristics, and the calculation here was done in characteristic 0 by Josep Montanel, by using some clever use of Meyer-Vietoris, multiple Myers-Vietoris. And so what do we see here? When we look at R mod this I, this is the ideal that is giving us this example, then you get this table of numbers, and the rows are going to be indexed by 0, 1, and 2 up to 5, and the columns are indexed by 0, 1, and 2 up to 5. And for example, this 2 over here is saying that the 5, 5, the 5,
We
5.
cannot see the example.
Sorry?
We cannot see the example.
Ah, okay. Let me fix that.
Screen has gone.
Okay, okay. I'm going to bring a new screen. Ah. Oh, sorry, not this one. Ah. Go away. Okay, give me another chance. PII, where's PII? Yeah. Okay. Can you now see a table of numbers?
Yeah.
Okay. So here's my regular ring. In this case, it's a power series ring, but it doesn't matter. Here's my ideal, this intersection of these three ideals. You can ask yourself, what are the Ljubetzig numbers of R mod I? And they're given by this table. So the table is indexed by rows and columns starting from 0. So this 2 over here is the 5, 5 Ljubetzig number, and this one over here is the 4, 4 Ljubetzig number. Now let's see if I can compute this for you. I'm going to go here. I'm going to share this screen with you. So I'm going to have to stop sharing this screen. Now I'm going to share another screen with you, which is what the tab. The tab is. So can you see Macaulay 2 now?
Yeah.
Okay. So I'm going to run some Macaulay 2 program. Maybe. Okay. Okay, so Macaulay 2 is thinking. I ask you to give me a Ljubetzig table, and here it is. So the 5, 5 Ljubetzig number is 2, and the 4, 4 Ljubetzig number is 1, and so on. So these are all the non-zero Ljubetzig numbers that correspond to this example in the literature I just showed you. And notice, and this is the thing that is very encouraging, so we're doing a calculation on the local cohomology module of a local cohomology module, which is a ridiculously big object. But it took us less than 5 seconds to produce this Ljubetzig number. So this works, not only this method works, but it's feasible. It actually produces answers after a few seconds. Okay, so I think this is all I want to tell you. Thank you very much for listening to me.
Okay. Let's thank Professor Katzman. And if there are any questions, please.
Okay, I have a question. First of all, thanks for the interesting talk and for the possibility to compute these Lubeznik numbers with Macaulay. But I have a conceptual question. Namely, in case you compute the local cohomology with respect to ideal I, you need it as a step in between. Okay? You need it. You need the local cohomology of R with respect to your ideal I. Okay?
Not quite.
No,
So,
in your this is one step of your argument.
well, not quite. So what you need is a root.
Okay, you need the root, but you use in some sense you have to check this cohomology.
Right. Okay. I understand the question now.
Okay, and this cohomology is in fact the inverse limit of local cohomology, just by local duality. Because you are in a case of regular ring, you have local duality. So this is the inverse limit of the local cohomology in the maximal ideal of R mod I to something. Okay?
Okay.
And for the computation of this cohomology, you can use the Czech complex. And the direct and the cohomology behaves well because the modules are Artinian, so you have surjective maps in the direct in the inverse system. And this seems to me another approach for computing this cohomology. Did you think about that?
So yes, at some point I did some work with Wenliang Zhang, which tried to do something.
By the way, I called it, in some of my papers, I called it formal local cohomology.
Right.
And in some things, it behaves quite nice under these circumstances.
Right. So this is not the first time I compute Lubeznik numbers. So there's another thing you can do by going through check cohomology or direct limit of causal cohomology, and it works in theory, but it's not implementable. I mean, you would need to wait a long time to get answers. So at least.
Okay, but I'm not talking about implementation, but I talk about conceptual arguments for understanding Lubeznik numbers, and it seems to me this kind of what I call formal local cohomology could be a good approach instead of using this complex of generalized fractions.
So I should learn something about formal cohomology, because then I may be able to look at it and say, yes, you can go to Macaulay 2 and press a button. And
okay, thank you.
Okay.
Any other questions?
Yeah, I have a question. So the Lubeznik numbers were with respect to two iterated local cohomologies. Whether this can be done if you iterate once again, the Macaulay program will work.
Okay, so what I showed you can be generalized to finding the bus numbers of any finite F module, but the bus numbers associated with the maximal ideal. And that's because when you think of these bus numbers as the dimension of a circle, then the dimension of a circle of an finite F module is the same as the dimension of a circle of a root. Now, if you're looking at the bus numbers of other primes, that's no longer true. So you cannot read off the bus number of an finite F module just by looking at the root. You may need to go a few steps along the direct limit system.
Okay, thank you.
Any other questions? Okay, if not, let us thank Professor Katzman once again.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you very much, Moty. Adiós.
Adiós.
Hasta pronto.
Adiós.